But somehow this is okay. Probably we had low pass representation, but then if you have low pass representation and you know that the signal is odd, then the resulting signal must be odd. Yeah, and then you just perform transformation such that the resulting signal will be odd. Yeah, that you have at one part you have positive amplitude and another side you have negative amplitude. So there is nothing. It's not difficult. So I mean, it looks like that's something complicated, but it's not. So just keep in mind that it's very simple transformations. Just remember what happens when you have even signal and when you have odd signal. And when you have when you transform a filter response, then you don't normalize. Yeah, this a couple of things that you need to know about transformation. Okay, yes. I hope it answers this question.
Yeah, it's like for me, like I like at the very beginning you had the representation of load, like the in load pass in time. So if you take the like what I did was um, do the Fourier transformation, and I get the result, which is just if I have a C function at the end, I have a rectangular one in.
But okay, because it takes a little bit longer, I would propose to come back to this question at the end of our seminar. Please remember your question and we can continue talking about it. But now I would propose to go back to discrete modulation schemes. And if this part or any other part still have any questions, we can discuss, but after our main topic.
Perfect, Professor.
So let's go back to the topic that we need to discuss today. One second, we have some small technical problems. Okay, last time we continue our discussion about discrete modulation schemes, and we consider the typical example when you have unipolar transmission, you transmit. Was it? No, yeah, according to this, it was. No, yeah. The first example was bipolar, but then we considered unipolar transmission, and we have to analyze this scheme and say what is single error rate, what is bit error rate, how can we find it, what's the optimal scheme for reception for such signal, and so on and so forth. So, and also we said that we have for such representation of signal, you need only one basis function to represent it. And as a result, the receiver side will contain only one correlator with only one basis function. And we have shown that the signal after processing, after correlator, can be written as normalized or like 2 times energy per bit, average energy per bit under square root, times value of what we transmit. If we transmit bit 0, then we get 0. If we transmit bit equals to 1, then we get 2 times EB under square root. And our decision based on or like based on the decision if we receive voltage larger than specific amplitude, we make decision for 1 bit. For bit, for example, it was to 1 if it's larger, And if it's below, then we say that it was bit equals to 0. Then we have shown that we have, due to noise, we will receive not exact values as we would have for without noise, represented by these delta pikes. But with noise, we will have the whole range of possible amplitudes. And sometimes, even if we transmit bit equals to 0, due to noise, we will make decision that it was transmission of bit equals to 1. And what it means that we make errors. And we want to understand how often we make errors. And as an answer that in order to find error, probability of error, we need to calculate area under tail of Gaussian function. And we can, what I did then, I just wrote the expression for this analytical expression for this area. It is an integral from value threshold to plus infinity. And then we have Gaussian probability density function. And there we assume that we transmit bit equals to 0. And then as a result, I'm writing the expression for this green curve. And you see that we have this 0 mean. We said we didn't show it, but you can, I think we do it later, or even if we don't do it, it's easy to prove by itself that if you have wide Gaussian noise at the input of your receiver and you use optimal processing, I mean, if you use correlate-based receiver, then variance at the output will be equal to N0 over 2. It will be not wide anymore, but it will have variance equals to N0 over 2. And based on this, by the way, we also have shown that standard deviation of each probability density function will be square root of N0 over 2. And based on this, we can write the expression for probability of error. There we use information about variance as well. And by replacing by substituting quantity x squared over N0 as t squared, we can rewrite this integral in the form that will correspond to complementary error function. And then instead of this integral, because you cannot calculate analytically, instead of this integral, we use a complementary error function. And we see that actually probability of error depends on value of minimum distance and variance of noise. And what is actually makes sense, that if you have smaller minimum distance, then probability of error will be higher. And vice versa, if you have larger noise, it also will be higher. So afterwards, we performed some statistical analysis of transmission. So we first of all calculated what's the average power. And for this case, we see that average power just matches average, I would say, power per bit. But here we have this, because of normalization, we get this EB. And then we calculated energy spectral density of pulse shape and convolving, no, not convolving, but calculating autocorrelation of random sequence and finding corresponding spectral density of it. We finally get what's the power spectral density of the whole sequence by calculating product. And we get that we have such a representation. We have a C-square function, and at origin we have additional delta peak. So we continue today discussion. Yeah, by the way, are there any questions?
Professor, I have a question concerning the bit error rate. Which we
Yes,
have.
please.
So when we have we first of all calculated the bit error rate of, say, when we have a 0 and then a 1 is received, and then we also calculate the bit error rate when we have a 1 and then a 0 instead is received. So I was wondering this
No,
when we,
no. I mean, what do you mean that?
I mean the probability of error.
Yes.
Assuming we transmit given S1 is S1 when S1 is received, given Y1 was transmitted, and then S2 given Y1. I mean, we have two probabilities, the two tails of the Gaussian distribution. That's what I mean.
Yes, and this is what is shown here. This is the first part, first tail, and we have another tail. Yes.
Yes, and we assume that both tails are equal. So I was wondering, I thought the total probability of error was going to be 2 times the probability of each of the tails.
I mean, it will be summation, but then also you should take into account probability of transmission of symbol itself. And probability of transmission of symbol is 1/2 because you have 2 possible options. And because if you don't do this, you will get that probability might exceed 1. It might happen that this probability will exceed 1. Just you can imagine the situation if you flip these two probability density functions. That for some reason something happens wrong, and then for all, like, for some reason, this is what you will get when you transmit S1, and this is what S2. And then whenever you place threshold, you will always get the highest possible error. And if you don't normalize, then in this case, you will get probability of error will be 2. Yeah, but of course it's not possible. The probability cannot exceed 1. And for this reason, we also normalize by probability of appearance for symbol itself. We multiply by 1/2. And in this case, it will be perfect case, and then probability of error will be simply equals to 1, because probability of error will be just the whole Gaussian distribution on the right side and another Gaussian distribution on the left side. Yeah, but we have area for one is 1, for another one also 1, and then if you calculate the summation 1/2 times 1 plus 1/2 times 1, it gives you 1. So this is just normalization in order to make sure that the final probability will never exceed value 1. Because if you don't do this, theoretically it might happen. So we take into account this here. This is the probability of symbol. We have to do this.
Okay, thank you. It's understood.
Okay, good. Yeah, any other questions? So, and yeah, it was all discussion. So let's continue. Today we're going to start with task number 6.3. And it's quite similar task to what we did before. But we have, instead of unipolar transmission, we will have bipolar transmission. And the task 6.3 already available in Moodle. So, and we repeat the same steps. So, and here we have 4 bipolar for 1. Okay, and our transmit signal is given by the following expression. Arbitrary energy is 0. It is instantaneous energy, our signal, and we don't know what the value of it. I mean, we know it, but it might vary for different. It might vary in time. So, and we have basis function, which is equal to 1 over square root of t. times rectangular pulse t minus capital T over 2. So divided by capital T. So this is our transmit signal. Z of n is nth symbol, and the amplitude of nth signal belongs to finite alphabet. These values -3, -1, 1, and 3. So we have 3 possible amplitudes in our alphabet. And also, you have, or you can find how many bits you can transmit using this alphabet. Because in order to encode each symbol, or we can say that we have 4 states, and in order to encode each state, you need to have 2 bits. And as a result, each symbol will carry 2 bits. So, and we use gray coding in order to encode our symbols. So we can also say that we use very simple lookup table. So if we have 2 zeros, we get value -3 for transmit symbol. If we have 1 0, then we get value -1, 1 1, it will be 1, and 0 1 gives us 3. And as you can remember, for gray coding, 2 adjacent states have difference only in 1 bit. If you look to adjacent rows, you notice that difference will be only in 1 position. And this is purpose of gray coding. If you take another 2 rows, adjacent rows, you also notice that difference will be only in 1 position. And then third, again, only 1 bit different. And also we can also look if we have first and because it's cyclic. So if you look to first and last row, difference also will be only at 1 position. And this is it was technical solution to solve problem with relays that used at the very beginning of such discrete systems. Okay, so what we know, since pairs of 2 bits are mapped to 1 single for the symbol with 4 states, the modulation interval T is twice as large as the bit interval. Okay, in the following, we first assume one-shot transmission. We consider only the transmission of the symbol Z0. It is assumed that the transmission is being disrupted by AWGN with fast density N0 over 2. Thus, received signal is a mixture of signal component and noise component. And we have 4 different possible signals. So first of all, we need to sketch our signals that we transmit. So we need to make sketch of signals, then and then we can discuss what we need to do next. So let's do it. We have 4 possible amplitudes, and we have the same basis function. So, basis function is just rectangular pulse. So it's rectangular pulse with amplitude square root of E0, square root of E0 divided by capital T. And square root. And also we multiply by value of the corresponding symbol. Let's say it will be our first signal, and we just take first amplitude in our table, -3. So we take and multiply by -3 square root of E0 under capital T. Now divide by capital T. So this is our first signal. Then we can continue, and it doesn't take too much time. You just do it and don't speak as I do. And of course, I made mistake because we have negative amplitude.
Hi, good morning.
Good
My last
morning.
one here.
So
Maybe she can come to my office once she's here. Okay, thanks. I need to
Okay, yeah. Let's continue. So yes, it's of course it's negative amplitude, and then for second signal we have amplitude -1, and we just show that we have -1 times square root of E0 times capital T minus square root of E0 capital T, and we continue. So then we have third signal as 3T and square root of E0 under square root. So we got this +1 times square root of E0 divided by capital T, and so on. As 4T and 4SOT. We get 3 times square root of E0 divided by T, and so now we have sketches for all 4 possible signals. Okay, that was not difficult. Then we go to B, where we need to draw the signal space diagram. So it's also easy because we have only one basis function, and as a result, all signals will lie or will belong only one line. So we just specify 0 somewhere on this line, and then we need to show one unit of some quantity, and this quantity will be square root of E0 minus square root of E0, and that's 3 quantities of square root of E0. Actually, I could take the larger scale. Like this. Square root of E0, 3 square root of E0, then we have minus square root of E0, and we have minus 3 square root of E0. Now, and this is our signal space diagram. Okay, we can also say that actually we can show that we have vectors that going from 0 towards this point, but all of them will be on the same line. Okay, now we have signal space diagram, and if we go to part C, we need to determine the minimum Euclidean distance between the signal vector depending on the mean energy per bit EB. So minimum distance, and here we can denote it, this minimum distance between signal vectors. But also we need to specify axis in terms of mean energy per bit, EB. And we don't know what's the mean energy per bit. And typical algorithm is the following. First of all, you need to calculate, as far as you're operating on symbols, you need to calculate what's the mean energy per symbol. And then based on information, how many bits you have for each symbol, you just calculate mean energy per bit by dividing it, mean energy per symbol by number of bits in every symbol. So mean energy per symbol, of course, it will be just summation over all possible or over all energies in our alphabet by number of this is number of elements in alphabet M. And so what's energy of each component in our alphabet? Remember that we have in amplitude square root of T. So then when we multiply, when we calculate integral, this capital T will be cancelled. And we get the following, that we have 1/4 is number of, we just divide by number of symbols. Then we have minus 3 square root of E0 squared plus minus 1 times square root of E0 squared plus 1 times square root of E0 squared and plus finally, I think I missed line, but anyway, 3 times square root of E0 squared. So this is what we have. This is our energy of each component. And what we get 9 E0 plus E0 plus E0 plus 9 E0. What gives us 20 E0 divided by 4. And the result will be 20 E0. This is our energy. Oh, not 20, sorry, 5. 5 E0. It is our mean. Mean energy per symbol. So this mean energy per symbol, but the question was we have to find mean energy per bit. But it's not difficult to find. We just take our mean energy per symbol and we divide by logarithm of 2 by number of components in our alphabet, or simply speaking, how many bits you have inside every symbol. So, and then we simply take our energy symbol and divide by 2, because we have 2 bits in every symbol. And that's it. This is our mean energy per bit in terms of this instantaneous energy E0. But then we might want to actually replace E0 in original, everywhere in original schemes and figures. And then we have to, instead of E0, use the following quantity, 2 times EB divided by 5. This is how we can represent E0 in terms of average energy per bit. Okay, fine. And but let's go back to our original question. We had to specify minimum distance in terms of average energy per bit. And minimum distance itself, as you can see from signal space diagram, I mean, you can just look to this signal space diagram and find what's the minimum distance. Just analyzing this picture. And of course, it will be 2 times E0 under square. So, and then you can just replace E0 by the quantity that we have found above. And you will find what's the minimum distance in terms of average energy per bit. But also what I do, I will take these 2 and I put it inside square root of it. So as a result, it will be 4 times 2 times EB divided by 5. And it will be 8 over 5 times EB under square root. So this is our minimum distance in terms of mean energy per bit. So this is how we do this. Do we need to find anything else? No. So let's go further to part D. We need to draw a figure of the optimal detector based on correlator. Assume that the correlator output is denoted as Y bar. And then we need to complete the expression. What actually we do to make decision about different signals. So, as before, we have only one basis function. And as a result, our receiver will contain only one branch. So, we have input path. And at the input, we have mixture. We have Si of t plus nt. So we have desired signal and noise. Then this mixture we put to the input of multiplier. Well, we calculate product this basis function, and we assume that we have perfect synchronization. We know perfectly when the signal sequence starts. In real life, you have to do some additional pre-processing steps to find this moment. But for theory, we assume that we perfectly know when signal starts, and then we just have this reference sequence and our input signal perfectly synchronized. So then we have integrator that accumulates energy over interval t, but not tb, because t is duration of symbol. And afterwards, we get quantity y1 that we need to analyze. And depending on the value of y1 in the threshold block or detector, we make decision what was actually transmitted. So, and just let's revise how transmitted signal will look like if you have only one symbol with index 0. We have energy, we have specific amplitude, square root of E0, times value of symbol with index 0, times basis function, just basis function. So our amplitude after processing, we calculate as integral from 0 to capital T. It is capital T, but not tau. Then we have square root of E0. Then we actually write mixture of our transmit signal, times basis function, and noise, plus noise. And this mixture we multiply with reference signal. And this reference signal is our basis function. So we have input mixture and we have reference signal. And we calculate integral over duration of symbol. So then we actually get that this result will be square root of E0 times Z0, integral from 0 to capital T, basis function squared, plus I think I actually wrote too much, but it's fine. It's fine. We can use it later. I will move it down. I will move it down. So we split it for two parts. At first integral, we have basis function squared, and for second integral, we have that's integral from 0 to capital T, and t times psi 1 of t dt. This is general form what we have. So first integral equals to 1, because it's just integral of basis function squared. And second integral, we say that it corresponds to an equivalent effective noise n tilde t, which will be 0 mean and variance n over 2. So, and as a result, we can write as E0 times Z0 plus effective noise. So, but if we assume that we have without noise, our output amplitude will be simply square root of E0 times Z0. This is what we get without noise. I can also show on the signal space diagram that you have what the amplitude to receive in different cases. So we have minus 3 square root of E0 under square root. We have minus 1 square root of E0. We have 1 square root of E0, and we have 3 square root of E0. So, and now we need to make decision, or no, we need to, yes, we need to make decision about where to place thresholds. And in our course, we use very simple strategy. We just place thresholds in the middle between adjacent symbols. So we have, where are the symbols? We have symbol 1, symbol 2, symbol 3, and symbol 4. And then we just take symbol S1 and S2 and place threshold right in between. And what's the amplitude? This middle point between these two symbols. It will be -2. Like -2 square root of E0. So it will be threshold between S1 and S2. Between then we go to symbols S2 and S3, and also we place threshold in between. In this case, this threshold will be at 0. And when we go to symbols S3 and S4, do the same. And our threshold will be at amplitude 2 times square root of E0. This is our thresholds that we use in order to make detection, perform detection. And this is Y1. And now we can write in which cases we make which decisions. So we say that our decision for S hat of t is the following. We say that we receive a signal S1 of t if Y1, it's only one, but yeah, if Y1 will be smaller or equal, let's say, -2 square root of E0. I can show this. Oh. For all amplitudes that will be smaller than threshold, we say that they belong to signal S1. Okay, fine. If for S2, we have more interesting condition that Y1 must be smaller or equal than 0, but it must be larger than -2 square root of E0. So if we satisfy these conditions, then we say that we have received signal S2 of t. Okay, and we also can show on the picture how it looks like. Now we have this second decision range. So whatever we receive, this amplitude in this range, we say that it belongs to signal S2. Okay, good. Then we go to S3 of t, and if our voltage after crossing will be smaller than 2 times square root of E0, but larger than 0, then we say that we have received a signal S3. And finally, for S4, we say that we receive signal S4 if amplitude will be larger than 2 times square root of E0. So we have, this is for S3, this green area. Green area for S3, and then just area without color for S4. This is how we make decision of what we transmit. Okay, this is how it works, and this is our rule for detection. Then we need to sketch. We need to sketch 4 conditional probability density functions. There is small typos, and for I goes from 1 to 4 in one and the same diagram, and we need to specify the most important parameters. So we can use this expression that I have derived above, this one, in order to understand what happens. First of all, we again, the resulting amplitudes might be different from signal space diagram, and you should be careful about it because it depends on what kind of receiver you consider. So, but nonetheless, let's try to understand what we get. So I will show that this is our output voltage, and we have different points. This is, by the way, this is 0. Okay, when we have 4 points, and I can say that each point corresponds to different signal: S1, S2, S3, and S4. So let's try to understand what the voltage we get without any noise. So if we substitute instead of Z0, -3, -1, 1, and 3, we get the corresponding voltages, or whatever units you will use for transmission to describe the received signal. So we get -3 square root of E0 under square root, -1 square root of E0, 1 times square root of E0, and 3 times square root of E0. And without noise, you will get delta pulses. Delta pulses without noise, because there are no any other voltages, possible voltage that you will receive. I mean, without noise, everything is clear. If you receive something around -3 square root of E0, it definitely will be signal S1. Because you don't have noise, you have no any disturbances during your transmission. But with noise, situation will be more interesting. You don't have nice delta X anymore. You will have the whole range of possible voltages. And this range we show with this probability, this bell-shaped function that correspond to probability density function of noise. Now I should choose actually different colors to make it more clear. So let me use maybe gray color. This is the range of voltages that we receive when we transmit signal S1. Then when we transmit signal S2, we have another range of voltages. Then for S3. And finally, this is what we get when we transmit S4. And you don't have only one possible voltage, but as again, you have the whole range of possible output voltages. And also specify thresholds. Our thresholds I just want to remind you that first threshold at position -2 square root of E0, second threshold at E0, and third threshold is at 2 times square root of E0. We have 3 thresholds. Also, we can specify what's the variance on our conditional probability density functions. Or actually, we can specify standard deviation. Sigma n will be equal to n naught over 2 under square root. And also, I have to label each conditional probability density function, because each conditional probability density function has specific transmit symbol. This gray curve corresponds to output voltages Y1 when we transmit signal S1. Green curve corresponds to, maybe I should place it above because I don't have space otherwise. I put it there, and I say that green curve corresponds to F voltage of Y1 when we transmit S2. Then purple is probability of density function of voltages Y1 when we transmit S3. And the orange one, F Y1 when we transmit S4. So depending on what we transmit, we have different conditional probability density functions. So what else we have to specify? Energy knows at all. Also, you can write, if you want, you can also use, instead of x squared of E0, you can use energy in terms of average energy per bit. You just need to go back and remember that square root of E0, or E0 equals to 2 times EB divided by 5. And we can use this expression to replace square root of EB. We can write it as minus 3 2 times EB divided by 5 by under square root. Then we have minus 1 2 times EB divided by 5 under square root. We have 1 times 2 times EB divided by 5 under square root. And the last one will be 3 2 times EB divided by 5 under square root. We can use such quantities instead of instantaneous energies. But I mean, it doesn't change anything, it's just different notation. So let's go further, and we come to the question F. We need to specify the integral expression of the symbol error rate as a function of d-mean. As a function of d-mean. And actually, it simply means that we need to specify. We just need to take specific. In our case, we just take specific symbol error rate and we express it as function of d-mean. EF. And let's get started. So, as before, we have different possibilities to make error, and we have different areas, tails under the Gaussian probability density function. But for simplicity, we consider only one possible case that corresponds to the situation when we transmit signal S1. We transmit signal S1, but for some reason, we received and made decision that was transmitted signal S2. And we consider probability of symbol error when we transmit first symbol. We need to calculate this area of green tail. And we can write, just remember that we know all parameters of this distribution. We know what's the variance, what's the mean value, and of course we can calculate, at least we can write integral expression for this table. And we can write it, I will write it in terms of average energy per bit. Okay, minus threshold will be minus 2 times EB divided by 5 under square root. Lower limit, upper limit will be plus infinity. And then we write expression for probability density function. We have 1 over 2 pi n naught over 2 under square root times exponential function of minus, in numerator we have x minus mean value, and mean value is minus 3 times square root of 2b divided by 5. X minus 3 times 2 times EB divided by 5 under square root squared divided by denominator, and in denominator we have 2 times variance and not over 2. This is our expression for n of course times dx. This is our expression for area under the tail after threshold. And now we need to represent this expression as a complementary error function, and we have to substitute some parts, and we need to rewrite this integral in order to match formulation of complementary error function. We do the following: we take our argument of we take numerator, the whole argument of exponential function, and we call it as t squared. So we have x minus 3 2 times EB divided by 5 under square root squared divided by n naught, and we say that the whole expression we denote as t squared. And then, it should be x plus 3, not minus. And then we get that x plus 3, 2 times EB divided by 5 under square root divided by square root of n naught will be equal to variable t. And if we calculate the differential, we get that 1 over n naught under square root times dx will be equal to dt. This is already the result we can use, but we also need to understand what happens with limits. If we make this replacement, we need to recalculate limits, and we know that in case of x, when we operating on x, lower limit for x works minus 2 times EB divided by 5 under square root. And when we make replacement, we need to recalculate. So we have to take this x and substitute it as the expression on the left side. And if we do this, we see that in this case, t, the corresponding t, will be 2 times over 5 times EB. No, EB divided by n. And the whole expression under square. This is corresponding to this new variable lower limit. And when x goes to plus infinity, we get that actually t also goes to plus infinity. So at least upper limit will be the same as before. Okay, now we can just put it in box. This is how we substitute variable. And now we need to rewrite our integral. So we write that it equals to integral from, and we take this lower limit, 2 times over 5 times EB over N0 under square root 2 plus infinity, and expression we have 1 over pi times N0 under square root times exponential function of minus t squared times, and also remember that in order to replace dx, we have to take N0 and multiply by dt. For this reason, we have this additional part, N0 under square root times dt. And what we can do, we can cancel N0 and N0 under square root. And in order to simplify further steps, I will multiply and divide this integral by 2. And what I do, I will take this upper 2 in numerator and put it inside integral. And then if I write it, write the result expression, it will correspond to definition of complementary error function. 2 over 5 EB over N0 plus infinity 2 divided by pi under square root times exponential minus t squared times dt. Now this is definition for, as I said, complementary error function. And as a result, we can simply use, instead of the whole integral, we say that it equals to 1 over 2 complementary error function of 2 over 5 times EB over N0 under square root, and that one. So this is what we actually get in the end. So we have this complementary error function that we use in order to find probability of symbol error. This is specific probability of symbol error. This is probability of symbol error when we transmit symbol 1 and we get symbol 2 instead of it. So just keep in mind, this is what it is. But also we can rewrite this expression in terms of d mean is 1 over 2 complementary error function d mean over 2 divided by N0 under square root. And surprisingly, you see that actually we get exactly the same expression as last time. It's exactly the same. And moreover, you can show that for any binary transmission, the probability of symbol error will depend only on minimum distance and variance of noise, and nothing else. And always it will be the same expression. Yes, d mean over 2 divided by square root of N0. So yeah, surprisingly enough. Next, what we're going to show, we're going to demonstrate, or we're going to find what's the symbol error rate in general. In general, regardless what the pair of symbols we consider. And then we find probability of bit error. Let me find this task to solve. Okay, now we have symbol error rate as function of EB by using complementary error function and so on and so forth. So it solves all together F and G. And then we come to H. We come to part H. So, and now we need to analyze. We have interesting result. And result is the following, or not result, but observation, that when we transmit signal S1, you have only one possibility to make error. So this possibility to make error will be represented by this green tail. But if you transmit signal S2, you will have two different possibilities to make error. First possibility represented by yellow tail on the left side, because you confuse your signal with S1. But there is also another possibility to make error, because when you transmit S2, you might make decision that instead of S2, you will receive signal S3, and you have another tail. And as a result, possibility to make error when you transmit S2 will be larger than possibility to make error when you transmit S1. Yeah, because you see, we have these 2 times more regions where you can make error. And we have to take into account this fact when we calculate average symbol error rate for this transmission. So actually, I'm going to do the following. I'm going to write what's the probability of symbol error for different transmissions. So when we transmit signal S1, we have the following possibility to make error. We have possibility that we have received signal S2 while we transmit signal S1. And we know what is this probability of error. We have found it. It will be 1/2 complementary error function of d mean over 2 divided by n0 underscored. So this is a possibility to make error. Okay. Then let's go to second symbol. So let's say we transmit symbol 2. And as I have shown above, you have one possibility that you will receive signal S1 while you transmit signal S2. And another possibility to make error that you made decision that it was signal S3 while in reality you transmitted signal S2. And we have to write it. Yeah, we have to wait a little bit. Let's continue. So we say that we have probability that we get signal S1 while we were transmitting signal S2 plus. So this is slightly different from what we did before, yeah? Because here we do not normalize. At this point, we just calculate summation plus probability of S3 when we transmitted S2. And each probability can be described by the expression that we derived previously. It will be 1/2 complementary error function d mean over 2 divided by n0, square root of n0. And I will write it as 2 times 1/2 complementary error function. It doesn't make sense what I wrote about it. Error function complementary. Error function complementary d mean over 2 divided by square root of n0. Like this. And we continue. Now we consider what's the probability of symbol error when we transmit signal 3. We have for signal 3. Signal 3. This is the area where we make error when we transmit signal 3. And again, you see that we have on both sides, we have possibility to make error. And also we say that we have, first of all, possibility that instead of signal 3, we make decision for signal 2. And on another side, instead of signal 3, it might be case that we decide that it was signal S4. Okay, so let's wait a little bit. Okay, S2 when we transmit S3 plus probability that it was S4 when in reality we transmitted as free. And again, each probability can be described as 1/2 error function of d mean by 2 divided by square root of n naught. And now we have it. And finally, probability to make error when we transmit signal 4 is simply that instead of S4, we made decision for S3. And nothing else. And we have just 1/2 complementary error function d mean over 2 divided by square root of n. So, and now we need to find average probability of symbol error. And we use exactly the same expression as we did at the previous seminar. Average probability of symbol error will be the following. You take probability of I will write it in general form. It will be summation I goes from 1 to m, probability of transmission of signal Sy times probability to make error when you transmit signal Si. Yes, and now we just need to substitute all what we know. First of all, very important point that for our task, we assume that all symbols equally probable and independent. And if you have 4 possible symbols, probability for 1 will be 1/4. So I will simply write 1/4 for probability Si, and it will be the same for all symbols. And what will be different or might be different is probability of Si, to make error for Si. So what we get? We get that we have 1/4, and okay, let me write in general. We do 1/4 probability to make error for first symbol, for second symbol, for symbol 3, and for symbol 4. And then we just use expressions defined above. But what we can do in order to reduce amount of writing, we see that in all 4 expressions we have the same error function, complementary error function, and what's different is just scalar in front of it. And we just put outside parentheses error function, and we consider only scalars. So what we get? We have 1/4, then inside parentheses we have, I even put outside parentheses 1/2 times error function rather than just error function. And inside parentheses we get 1 plus 2 plus 2 plus 1 times 1/2 complementary error function d mean by 2 divided by square root of n. Okay, and you see that this summation inside parentheses will be 6/4 times 1/2. We get, and I can write it as 3/2 times 1/2 complementary error function d mean by 2 divided by square root of n. So it simply says that for such transmission, error function will be 1.5 times larger than in case of bipolar transmission. This is the point. But it will be, symbol error rate will be larger. But now let's look what happens with bit error rate. Because you see that symbol error rate will be larger, but it's also interesting, but how bit error rate will change in this case. And in order to find it, we can use very simple expression that because, yeah, it's it's worth to say that here I consider, or I assume it's so-called, how it's called? It's called nearest neighbor approximation. And what it means? It means that when we make mistake in our transmission, mistake happens only between nearest neighbors, only between points, only between adjacent points. And we don't consider cases when we have errors between distant points. For example, if we transmit S1 and we made decision that it was S3, we ignore such cases just for simplicity, to simplify our notation. And for this reason, this is why I considered only pairs, only adjacent pairs. But actually, I also could consider pairs, more distant pairs, but I didn't, because I just assumed that probability for such events is negligibly small. Okay, and for such scenarios, for such situation when we have only nearest, when we assume nearest neighbor approximation and only error between nearest neighbors, probability of bit error can be written as probability of single error divided by logarithm 2 by n. Because if we have error between adjacent symbols, it means that we have that mistake occurred only in one of bits, because remember that two symbols different only in one bit. And if we, instead of one symbol, make decision for another one, it means that the problem only is one bit out of all possible sequence of bits that we transmit with each symbol. And this is expression, this is approximation, just to be clear. And if we calculate, we get that bit error can be found as 1/2 times 3/2 times 1/2 complementary error function d mean by 2 divided by square root of n. And what it gives us the following, that 3/4 times 1/2 complementary error function d mean by 2 divided by n0. Now let's compare this result with what we had before. But okay, before we come to comparison, please pay attention that now in front of expression for bit error, we have 3/4. And it means that it will be smaller, that the resulting probability of bit error will be smaller than 1/2 of error function itself. So, and if we go back to our expression before, for previous task, this is what was our probability of bit error. Oops. Oh, unipolar TX. So you see that now we get probability of bit error smaller than it was for previous case. And it actually tells us that it's probably more efficient to use for PAM modulation rather than to use bipolar transmission. Yeah, that even we see that the symbol error rate is higher, but bit error rate will be slightly smaller than for uniport transmission. This is interesting observation, interesting results. Okay, are there any questions before we go to the rest of the task? Okay, let's go next. Go to part I, and there we have the following. Now we assume the transmission of a continuous symbol stream, Z of n. So instead of one symbol, we consider infinitely long sequence of symbols. And we need to find the mean transmit power P. P that equals to UTX squared averaged over time. This is question mark. This is what we need to find. And as far as we assume that all these symbols independent, and we have infinitely many symbols, and all of them have equal probability, we can simply use the following expression: 1 over m summation I goes from 1 to m of Si squared. So this 1 over m is probability of Si, and then Si squared is just what will be the corresponding squared value, what will be the corresponding power when we transmit ith symbol. And for our case, we have only 4 possible options. It's not difficult to write. We have 1 over 4. Then we have, if we have first signal, we have minus 3 squared plus minus 1 squared plus 1 squared plus 3 squared. We have 4 possible options for amplitude. But also you shouldn't forget E0. Okay, maybe I should rewrite it. I should write it actually as minus 3 times square root of E0 squared plus minus 1 times square root of E0 also squared plus 1 times square root of E0 squared and plus 3 times E0 squared. We have this expression, and if we calculate, we get that average power will be 5 times E0. 5 times E0. Okay, this is our average power. Then we go to part J. We need to find the discrete autocorrelation function of the symbol sequence, of such infinite sequence of symbols. So we say that our autocorrelation function for shift m can be found as expected value of original sequence Zn and shifted copy Zn plus m. So now we need to calculate expected value of such product. Okay, great. But also remember that as far as sequence is independent, we get that for this autocorrelation function will be equal to second moment of Z when m equals to 0, and will be first moment squared when m non-equal to 0. And what we get, that for second moment we get value 5 times E0, and for, because if you calculate first moment, you have minus 3, minus 1, plus 1, plus 3, and gives you 0. First moment will be equal to 0, and this is what we have here. M equals non-equal to 0. I can write the minus 3 square root of A naught plus, no, minus 1 over 4, minus 3, minus 1, plus 1 plus 3 square root of E0 and equals to 0. This explanation for this 0 value for our autocorrelation function. And then we can show that this discrete autocorrelation function, we have only one non-zero value at origin. So we have this discrete pulse at origin, and you have amplitude 5 E0, and we have discrete, we have index, discrete index M, 1, 2, 3, minus 1, minus, and so on, by ZZ of M. So this is autocorrelation function. Are there any questions? Okay, which is the difference between this power and the energy mean we calculate in point C? Let me check again what was at point C. Determine, no. Determine the mean increase in distance. Ah, yeah, there is no difference. Yeah, it's the same. But I mean, in C, you had to calculate, we also calculated energy, sorry. No, 1 second. First of all, in part C, if you would you could also calculate power in part C, and then we wouldn't have any difference. But in part C, we had to calculate energy. We had to calculate energy, but because we used normalized, we have to use normalized basis function, surprisingly, we get the same expression. But still, remember that in part C, we calculated energy. We calculate energy. Here, we're operating on power. And what we use here, we just take amplitudes. We take amplitudes and we don't take into account basis function. Because if in part C, where was part C? Let's go back to part C. At this point, okay, I didn't show it. I didn't show it explicitly, but you have to take your signal and calculate energy of it. So 1 point there, you calculate as integral of signal S1 squared over time from 0 to capital T. This is how we calculate every point in part C. But what's the difference? Or not the difference, but what's the result? For our signal, we use this basis function, psi1. And if you calculate integral of psi1 of t squared over time, 0t, it gives you 1. But if you would have, instead of this basis function, just rectangular pulse, t minus t over 2 divided by capital T, dt. What will happen in this case, squared? You will get that this integral will be equal to capital T. So you get exactly the same number, but be careful because meaning might be different. Meaning might be different. And for part C, we were talking about energy of the whole signal, but now we're talking about power, and we don't take into account duration of our signal. This is the difference. But I agree that numbers actually just the same. Okay, so I hope I answered this question. So finally, we have K and L. So K, in the lecture it will be shown that autocorrelation function can be found from discrete version. And actually what it means, it says that if you want to find autocorrelation function of continuous time discrete sequence, Then you have to normalize your autocorrelation function. I show that. I will just copy the autocorrelation function above. Oh, what's that? And then we convert M to delay. And what actually happens is we have to normalize our amplitude by spacing between symbols. So, and as a result, instead of discrete pulse, you will get Dirac delta pulse with magnitude 5E0 divided by capital T. But for all other points, we still have 0. We still have, sorry, it's not 0, it's 0, capital T, 2 capital T, and so on. And the magnitude will be equal to 0. And this is delay. And we're talking about phi x delta time. This is what we get. This is the resulting autocorrelation function for continuous delay. So, and we also have to find corresponding to this autocorrelation function power spectral density. And I mean, it's obvious. See, we just a line. It's just a line that goes through the point 5E0 over capital T. And this is our power spectral density x delta f. Now we are in frequency domain 0. So, yeah, that's all. And this is we get it by Fourier transform. Yeah, nothing special. And finally, we come to part L. Part L. So let's see. The transmit signal also can be written as convolution. Okay, we already know that we can represent our signal as convolution between pulse shape and sequence of delta pulses, weighted sequence of delta pulses. Convolution is we have x delta t. Okay, fine. And we actually already know what's the autocorrelation for part x delta t. And we also know what's the power spectral density. We don't know, or it's supposed that we don't know yet, what's the autocorrelation and power spectral density for Psi1. So, and our goal is to find power spectral density for the whole transmit sequence signal. I mean, of course, we know what's the autocorrelation function for Psi1 of t, because we know that the basis function is just normalized rectangular pulse. I can just show that this is the question mark. I can show that the autocorrelation function for Psi1 of t is nothing else as rectangular pulse that goes from minus capital T to capital T. And what's the amplitude? The amplitude will be 1 over t. 1 over t. And then Fourier transform, if you want to find the power spectral density, energy spectral density, is psi square function. So, and the amplitude will be just 1. Just 1. And the 0 will be at 1 over t. like this. Pi u n. Okay, great. And now we just need to combine all what we know. We know that we have scalar in front of this whole expression E0, square root of E0. We know how the, oh, sorry, this is not UU, this is psi1, psi1. We know how energy spectral density will be for our pulse shape function. We know how power spectral density will be for sequence of symbols, random sequence of symbols. And now we just need to combine all these parts. Okay, so if we do this, we get that I can draw it. We simply get the chi-squared function. And amplitude will be E0 1 second, we get, yeah, Houston, we have got a problem. The problem that actually we don't need to have E0, but why did I write it 0? E0 n. Okay, we have small typo. It's not conceptual, but still there. Yeah, I mean, for part E, the question was about power. It was a question about power, and we have written square root of E0. There, it's absolutely right. Sorry, that's correct. Square root of E0. So, and we get power. But when we calculate our calculation function, it's question only about the n itself. And what we know about the n. So for the n, we have some units, and it's not specified what the units. We just have numbers: -3, -1, 1, and 3. And we don't have E0. So for this reason, I have to remove E0. And we have just the number 5. We don't have E0. It was a mistake. Sorry for this. So we have just numbers. They don't ask about powers, they're asking about symbol. So we don't have E0 anywhere. We have just 5 over T0, 5 over T0. And finally, we multiply by E0 because it comes from this expression. So and we write that our resulting power spectral density, our power spectral density for signal U and frequency domain will be E0 times 5 divided by capital T. This is what we get. So what else they might ask us? Yeah, or are there any questions? Are there any questions or any comments? I just try to check the consumer. Oh. So, and the last part, let me check. We can write out what will be the expression for this part. Cadence, we can write it as E0 times pi over FLC times psi squared function pi f capital T. Okay, I also check one more time. I will check one more time because I think there might be something wrong with scalar, but I will check it. I will check it, and next time I will let you know. Yeah, are there any questions beside it? Not? Then I think we already is a little bit outside our seminar. So, and if there are no questions, then I would like to say thank you. Okay, there's a question.
Yes, I would like to know about the last part. So what we did in the last part, it's actually same as taking the magnitude square of the Fourier transform of as we did last time.
Yeah, exactly. I mean, you can also do it as yeah, probably this is the place where I made mistake. I need to write it more explicitly. This is what we did exactly. What we calculated Fourier transform, or simply speaking, what we did, actually I did slightly different. I calculated autocorrelation function for pulse shape. I also have autocorrelation function for sequence x delta. And then I know that if I want to find resulting autocorrelation function, it will be convolution of these two parts. And then calculating Fourier transform, instead of calculating convolution, I will find pulse density. This is what was the algorithm. And this corresponds to energy spectral density of psi1 times pulse density for x delta f, and equals to pulse density that we had to find in our task. This is the part that I tried to follow. Because you know what's the autocorrelation function, energy, you know what's the autocorrelation function for stochastic part, and then you can simplify the resulting pulse density.
Thank you.
Yes, you're welcome. Yeah, other questions? Okay, if not, then I wish you a productive rest of the week. And do we have last tutorial next week? I think next week we have last tutorial, but don't worry if you feel that you need more tutorials. We can arrange extra tutorial for communications engineering, maybe also in the end of next week or maybe even following week. So we can also arrange extra tutorials if they will be required. Okay, so thank you for your attention and see you next
Okay.
week. Goodbye.
Yes.
Yeah, if you have questions, just to stay in the session.